Math, it's all about math, the wonderful world of math. Welcome to the wonderful world of math. Today we're going to talk about binomial coefficients using Pascal's triangle. So what is Pascal's triangle? Wait a minute, no, that's Pascal's triforce. So what is Pascal's triangle and how does it help us to expand a binomial? What is a binomial? Well, gosh, a binomial is a polynomial that has two terms. In its easiest case, we say the first term, and whether that is actually made up of more than one thing, like 2x or 4yz, it doesn't matter for now. The first term is just going to be called a, and the second term is going to be called b. And to expand the binomial means that we're going to take that binomial and raise it to a power. For example, a plus b parentheses squared means, well, what does squared mean? It means times itself. So a plus b parentheses squared means a plus b times a plus b, which means we're gonna FOIL. First times first, outside times outside, inside times inside, last times last. So that's, again, first times first, a times a, or a squared. Outside times outside, the two outermost, an a and a b, so that's going to be plus ab. Inside times inside, the two innermost, that's b times a, and then last times last, the two last in their respective binomials, b times b, or b squared. Now you'll notice that ab and ba are the same because of the commutative property of multiplication, so that a plus b parentheses squared is going to be a squared plus ab plus ab plus b squared. But you'll also notice, hopefully, that ab and ab are the same. So what do you get when you take one banana plus another banana? Two bananas. This is a squared plus 2ab plus b squared. Now the thing about this lesson and Pascal's triangle is that we want now to pay attention to these coefficients. What is the coefficient of a squared? Well, it's got to have some coefficient, right? What can I multiply by a squared to get a squared? The answer, 1. That's the number that's multiplying by a squared and is basically invisible, right? The invisible 1. The coefficient of ab, well, you can see that one. It is visible. B squared has another invisible 1 for a coefficient, right? So it's a little better. 1, 2, and 1. Those are our coefficients. Well, how do we expand this? A plus b parentheses cubed. Well, what does cubed mean? It means a plus b times itself 3 times. Now, we already know what the product of two of these is. We know this is a plus b squared, and we've just calculated it, we've expanded it, we've got this. So those first two turn out to this, and to get a plus b cubed, we still have to multiply by a third a plus b. So these guys turned into that. These guys times the third one is the same as this times the third one. So now we just have to multiply this. This is how we do higher powers, right? We multiply two of them together at a time, and then we multiply by another one, and then by another one. Blah. So it's not called FOIL because there's not just going to be 4 partial products. We're going to have to multiply a by each of these. We're going to have to multiply b by each of these. And that's one way to do that. And as we get bigger, it's going to be more and more of a better idea to try to express this with a box. We're going to multiply this with a what we call the lattice algorithm. We're going to have one row for each term of one factor and one column for each term of the other factor. It doesn't really matter which one's which. Just pick one and stick with it. So here we've got one row for each term in the second factor, and we're going to multiply this term by this term. So a times a squared is going to be a cubed, and a times 2ab times 2 times a times b, two a's and a b. a times b squared. ab squared. That was easy. And then on the next row, we've got b times a squared. So that's a squared b. And a b times 2ab. That's 2b's, 2ab squared. And then we've got b times b squared, or b cubed. You look for the ones that are like terms. And usually they show up on diagonals. That's a kind of a big diagonal there. That one and that one. And you add these up. You see these guys are like terms. These guys are like terms. 1 banana plus 2 bananas, 3 bananas. So this product is going to be 1a cubed plus a total of 3a squared b plus a total of these guys also, 2 bananas plus 1 banana, 3ab squared plus 1b cubed. So the coefficients are 1, 3, 3, and 1. Before we get on to the triangle, I want you to expand a plus b parentheses to the 4th power. You can do this a couple of ways. I'd like you to try to think of them first, and then, do them. So 3, 2, 1. Have you tried them? Last chance. You can try a plus b parentheses squared times a plus b parentheses squared, in which case the box method becomes even more helpful. Or you can take a plus b parentheses cubed, our answer from the previous slide, times the 4th a plus b. Either of these will get you a total of 4 powers of a plus b. So now, if you haven't yet, try to actually multiply these things out. And 3, 2, 1. We're going to do the second one here. A cubed plus 3a squared b plus 3ab squared plus b cubed times a plus b. Now, a times each of these 4 fellows, and b times each of these 4 dudes. We've got a times a cubed, a to the 4. A times 3a squared, that's a total of 3 powers of a now. And a times 3ab squared is now 2 powers of each. And a times b cubed. We've also got b times each of those guys, like we said. So this is going to be 3a squared b, 3a squared b times b. That's going to be a squared, 3, and now 2 b's. We've got b times 3a b squared, so that's 3a b cubed altogether, and b times b cubed, b to the 4th, yikes. And the one that I totally forgot because, there we go, a cubed times b is going to be a cubed times b. Marvelous. Now, when I add a times each of those guys plus b times each of those guys, I lined them up so you could see the like terms. A to the 4 plus a total of 4 of these guys, a total of 6 of these guys, and a total of 4 of these guys, and there was only 1 of these guys. That's what this looks like. That was one way, this way. And you can do this with the box approach, the lattice algorithm. That works great there too. Notice the coefficients. 1, 4, 6, 4, and 1. So by now we have enough to actually talk about Pascal's triangle. We're going to look at the coefficients, just the coefficients, no x's, y's, a's, b's, none of that. Just the coefficients of the expansion of the binomial a plus b raised to powers. A plus b raised to the 0th power. Anything other than 0 itself raised to the 0th power is 1. There's only one term if it's raised to the 0th power. It's just 1. That's it. End of story. A plus b parentheses to the 1. Well, anything to the 1st power is just itself, so you're just going to get a plus b. The coefficients are 1 and 1. 1a plus 1b. So you got 1 and 1. Now, this next one is the first one we did in this video. A plus b parentheses squared. When we did this, we got 1a, 2ab, and 1b squared. I said a. 1a squared. Yeah? Okay. So we're going to get 1, 2, 1. 1a squared plus 2ab plus 1b squared. Marvelous. Now what are the coefficients for a plus b parentheses cubed? Look it up. Okay, did you find it? We should have got 1, 3, 3, and 1. A plus b to the fourth. We did this one also. 1, 4, 6, 4, 1. Now, Pascal's triangle is what we get when we use this and establish the pattern. What do you notice about this triangle? You should notice a couple things. Number one, it gets wider each time you go down, right? Okay, good. You should also notice that the outermost coefficients are always 1. You might also notice that the next layer of coefficients is going up by 1 each time. But the really cool thing about Pascal's triangle is that I can find any coefficient in the next row by adding the two diagonal coefficients from the previous row. To get the 4, I'm going to add the 1 and the 3, and that's 4. The 6 is the sum of the two 3's above it. This 4 also the sum of the two adjacent in the row above. The same thing with these 3's, right? They're the sum of the 1 and the 2, or the 2 and the 1. So, for Pascal's triangle, for this triangle of coefficients, these outermost ones will always be 1. You should also notice that each entry is going to be the sum of the 2 in the row above, and that it's going to be symmetric. So let's figure out the coefficients for a plus b parentheses to the 5th power. Well, the outermost ones are going to be a 1 here and a 1 here. You'll also see that these guys add up to get you 5. These add up to get 10, 10, and 5. Try to do the next two rows. 3, 2, 1. We should have got this and this. So what does that tell me about, for example, a plus b to the 5th power? Well, let's see, what else do we notice about the actual polynomials, the expansions here? We'll notice that for every a plus b parentheses to the nth power, there's going to be n plus 1 terms. So here n is 1, 2 terms. Here n is 2, 3 terms. N is 3, 4 terms. Okay, good. You'll also notice that, let's take a look at this one. For each term, the exponent of a goes down from n, 4, by 1 each term until we have a to the 0. No a's at all, right? You'll also notice that the exponent of b goes up from 0 to 4. So no b's, 1b, 2b's, 3b's, 4b's. For a plus b parentheses to the 5th, we should expect the coefficients to be given by this triangle and the terms of the polynomial themselves to follow the pattern we just mentioned. 1 a to the 5th, or just a to the 5th, plus 5 from Pascal's triangle, 1 less power of a, 1 more power of b, plus 10 from Pascal's triangle, 1 less power of a, that's a cubed now, 1 more power of b, plus 10 from Pascal's triangle, 1 less power of a, 1 more power of b, plus 5 from Pascal's triangle, 1 less a, 1 more b, plus 1 from Pascal's triangle, b to the 5th. If you do this out the long way, if you multiply a plus b times itself 5 times, yikes, this is the polynomial you should get. So the variable parts are very predictable. A starts from n, the nth power of a, and goes down 1 each time. B starts from 0 and goes up 1 power each time. Coefficients, the numbers in front, given by Pascal's triangle. So right now, you should be able to fill in the 6th and 7th lines, or, okay, if we count this one as the first line, this would be the 7th and 8th lines. Sure. Fill them in. Are you ready? Did you get them? Even without multiplying this stuff all the way out, it still takes a long time. 3, 2, 1, reveal. So you can check your work. This is what we should get. So let's write down some things we've said and noticed. To expand a plus b parentheses to the nth power. There will always be n plus 1 terms in the expansion. That the exponents of a decrease by 1 from term to term, going from left to right, starting from n and going down to 0, and that the exponents of b do the opposite. They increase by 1 each term, starting from 0 going up to n. Also notice that the sum of the exponents of a and b in each term is always n. Here's a bunch of stuff to look at. The sum of the exponents, well, is 2 plus 0 is 2. 1 plus 1 is 2. 2 plus 0 is 2. The sum of the exponents here, 4 plus 1 is 5. 3 plus 2 is 5. 2 plus 3, 5. The sum of the powers of a and b in each single term will always be this same exponent. And the key observation for Pascal's triangle was that each entry is the sum of the two diagonally above it. Aside from, of course, the ones. You just always have ones on the outside. So this is Pascal's triangle, this triangle made of coefficients for binomial expansions. That's pretty cool. The huge drawback to this is that in order to get, say, the coefficients for a plus b parentheses to the 10th power, I've got to do all of the rows of the triangle in between the 7th, the last one we did together, and the 10th. If I want to do a plus b parentheses to the 20th, I got to do all the stuff in between. So in the next video, we'll talk about how to do that without having to do all the stuff in between. And that's called the binomial theorem. Pascal's triangle is really good for that pattern finding, low n approach. But when you have bigger n, it takes a while. So let's try an example where we actually have to expand a binomial more exciting than letter plus letter. Here we have two terms, 2x and 3. Expand 2x plus 3 to the 4th power. Essentially, what we're saying here is that 2x is basically our a, and 3 is basically our b. We're going to take the observations that we made here, and for the triangle of coefficients, Pascal's triangle, and we've got that we're going to have 4 terms. The first one is going to have binomial coefficient 1 from Pascal's triangle. And then we're going to take the first of these two terms, 2x, and that's going to have to be to the 4th power. 2x to the 4th power. We're going to have 0 powers of the second term. The next one, coefficient comes from Pascal's triangle, 4, and we're going to have 1 less power of the first term and 1 more power of the second term. The next term, coefficient comes from Pascal's triangle, 6. 1 less power of the first term and 1 more power of the second term. Plus, the coefficient comes from Pascal's triangle. If you said 4, good for you. 1 less power of 2x and 1 more power of 3. The next term, the coefficient comes from Pascal's triangle. 1, 4, 6, 4, 1. Hopefully this is starting to sound familiar. 1 less power of 2x means no more powers of 2x. And 1 more power of 3 means 3 to the 4th. This is something that we should now simplify. 2x parentheses to the 4, have to remember means 2 to the 4 and x to the 4. 2 to the 4 times x to the 4. Now here, this is a lot of numbers. 2 cubed times 4 times 3. Think about it. 2 cubed, 8. 8 times 4, 32. 32 times 3, yikes, 96, x cubed. Okay, the next one. 2 squared, x squared, 3 squared, 6. 2 squared times 3 squared, 4 times 9, 36. 36 times 6, whew, 216. Next one, 3 cubed. That's 27. 27 times 4 times 2, 27 times 8. Maybe that's too hard. How about doing this a different way? 27 times 2, okay, that's 54. 54 times 4, that's not that bad. 54 times 4, that's 50 times 4. that's 200, plus 4 times 4, 16. The fact that those are the same is kind of a coincidence. Don't read too much into that one. And then 3 to the 4th, 81. And there's our answer. Okay, next example. Expand u minus 5w parentheses cubed. This is different because we've got minus. What we have so far doesn't actually tell us how to address this. What we're going to do is we're going to do kind of a standard trick. Instead of saying minus, we're going to say plus the opposite. This is going to allow us to talk about this as if it were the same kind of addition we'd been doing. So now this is like saying A is just standard U, but B is crazy negative 5W. So we can proceed normally, right? We're going to have n plus 1 terms. If n is 3, then that means 4 terms. Which reminds me that I probably said in the last example that this meant we're going to have 4 terms. That's super wrong, as you can tell. It says n plus 1 terms, so 4 equals n. Clearly there are 5 terms. Here, n equals 3, n plus 1, 4 terms, right? Each time you're going to have 1 less power of A and 1 more power of B. A starts with the third power. So the first term, U to the third power. 0 powers of B. And the coefficient of this guy, oh, let's scroll back. We've got, in A plus B cubed, 1, 3, 3, 1. So this first guy has a coefficient of 1. The next guy has a coefficient of 3. 1 less power of U means U squared. 1 more power of B means 1 power of negative 5W. The next one, 1, 3, 3, 1. This is going to have a coefficient of 3. 1 less power of U, and 1 more power of B. So negative 5W squared. Plus, wait for it, 1, 3, 3, 1. 1 less power of U means no more U's. 1 more power of negative 5W means negative 5W parentheses cubed. Simplify. Positive 3 times negative 5. Negative 15 U squared W. Negative 5 times negative 5, positive 25. And positive 25 times 3, positive 75 U W squared. Negative 5 times negative 5 times negative 5, negative 125 W cubed. And there we go. Notice that when we have a negative here, the effect was that the signs of our terms alternate from positive to negative to positive to negative every time they alternate. Alternating means the signs switch every time from positive to negative and then back, right? So can you try this one? 3x squared minus 4y parentheses to the 5th. Pause it. I'll wait here. Okay, are you ready to go over it together? N equals 5. That means that there are 5 plus 1, 6 terms. The first term is 3x squared. The second term is what we're going to think of as negative 4y. So when we say there are n powers of a in the first term, that means that I'm going to raise this whole business, parentheses, to the 5th power. The coefficients for this, if n equals 5, that means that we want the row that says a plus b to the 5. Coefficients, 1, 5, 10, 10, 5, and 1. 1. 5 powers of a to start with means 3x squared parentheses to the 5. Then we've got the coefficient 5. So 5. We've got 1 less power of the first term and 1 more power of the second term, and so on. If you got stuck the first time, this is a hint. Please give it a second shot if you need to, because I'm going to kind of skip to the next step. Here's the rest of it. As you can see, the coefficients follow the pattern set out by Pascal's triangle. Each time we're taking 1 less power of 3x squared and 1 more power of negative 4y. Now, when we multiply all this stuff together and simplify, we should get this. That is the expansion of the binomial. Notice again that the sign of each term alternates from positive to negative and back again. So that's it. We're done. We'll see you next time when we talk about the binomial theorem. Our constellation of the day is chameleon. Maybe a chameleon named Pascal? This has been a Badger Bear production of the wonderful world of math. And no, Pascal's triangle is not named after Rapunzel's companion Pascal from Tangled. No, it's named after Blaise Pascal, the French mathematician and philosopher. But you probably weren't worried about that. Good night, and see you next time. Same reptilian time, same reptilian channel.